Okay, welcome. So I already started to fill out the whiteboard, but this is some information that in principle we already talked about. So I want to quickly review that. So that was the idea of writing down an effective form of the free energy that's not written in terms of the microscopic variables. So for the Ising model, the microscopic variables would be individual spins, but in terms of some coarse-grained order parameters. So here the order parameter in the case of the Ising model is the magnetization M. Remember that an individual spin can only be in the Ising model, can only be plus or minus 1. But since the magnetization is an average, the magnetization can now be any real number, any positive real number, plus or minus. Okay. So M is some continuous real variable. And so the idea of Landau is to take the free energy density, so the free energy is some volume integral of the free energy density, and expand it out in terms of the local magnetization. Again, you should think of the local magnetization as the magnetization you get from somehow drawing a little sphere around this point where you're looking and computing the average in the vicinity of that point. And again, it makes sense because atoms are very small. So you can imagine that this would be a sphere that has a radius of God knows what, a micron or something. So it's a very small radius so that you can treat this as a local variable, but it contains many, many spins. So it makes sense to average. So this is, again, the magic of having 10 to the 23 spins. So Landau says, let's just expand it out. So it's expanded out as a polynomial. And in this case, it only has even terms because the macroscopic Hamiltonian of the system is even under the inversion of spin. So the average magnetization must still remember that. Where in this particular case, by the way, so there is a term that's odd in M, and that appears if we add an external magnetic field. So in that case, there is a term M times H, and that one is linear in M because the magnetization, the external magnetic field, knows the difference between up and down. So I write it down to fourth order, and you see from the diagram below why we need to keep at least fourth order terms. And that's because in order to capture the idea of a phase transition, we must allow for potentials where just alpha changes sign, because if alpha is positive, then the minimum of the magnetization will occur at 0. But if alpha is negative, then the minimum of the magnetization can occur somewhere else. And then, of course, it needs to be stabilized by a positive fourth order term. Now, you can add higher order terms. You can add terms like m to the 6 and m to the 8 and so on, and that's indeed sometimes done. But you can convince yourself that since when the magnetization initially turns on, so we get this kind of behavior. So this is magnetization as a function of temperature. We saw that we get this kind of curve, like so. So the Landau theory is strictly applicable only in the vicinity of the phase transition. So it's strictly applicable only here. So in this regime, you're always allowed to assume that m is small, and you can indeed see that if you include a higher order term, that will not change the functional form of m as a function of t in the vicinity of Tc. It will change it as you get further and further away from Tc. So you can view these higher order terms as providing more accuracy if you go away from Tc, but arbitrarily close to Tc, you're always allowed to ignore them. I mentioned again that these alpha, beta, gammas, you should view them as functions of the other thermodynamic variables. And in particular, you should view them as a function of the temperature. But again, since we're constructing a theory that's relevant close to Tc, you're allowed to Taylor expand them in T minus Tc. And here this coefficient alpha is special because, again, in order to have a phase transition, alpha must change sign. So near Tc, the constant term is absent, and then there's some term linear in T minus Tc, whereas the other coefficients, they just have some value at Tc. And again, you could try to increase accuracy by keeping more terms, but qualitatively, you can just replace them by a constant. And so you obtain this kind of free energy functional that's shown here at the bottom. Again, the magic is that above TC, alpha is positive, the minimum is down here in the middle, and then you develop a minimum that's at some finite magnetization. But because the potential is even in M, it automatically has two minima. And so the system will have to spontaneously choose one. And one of the ways in which it can choose is if indeed you keep this term that has the magnetic field. So that will effectively provide a small tilt to this potential. So if you keep the magnetic field, then one minimum will be a little bit lower and the other minimum will be a little bit higher. There will be some slight tilt to this potential. Okay, so this is what you get. If H is greater than 0, then one of them is preferred. But at exactly H equal to 0, so you can imagine turning the H on, then the system has a definite minimum, and then you slowly turn it off. But then now the system's, of course, stuck in that minimum. And so then it has effectively chosen one of these two possibilities. And as I mentioned earlier, that's the situation we refer to as spontaneous symmetry breaking. Okay, so that was a kind of mini review of the Landau functional. And if there aren't any questions, I was going to move on to an interesting application of this. So, so it is, by the way, it's sort of one of the, I think the Cessna book is a beautiful book, but one of the oddities of the book is that there's a lot of interesting information that's hidden away in one of the problems. So the book sort of implicitly assumes that you work through all the problems. And so this whole Landau functional, which is indeed an important thing, is hidden away in one of it. There's a long, long problem in chapter 9. And so one of the ways you can read up on it, on the Landau idea in the textbook, is indeed if you read through that problem set, which, I think effectively just reiterates what I'm saying here. But okay, if you want to read about it, it actually is in the textbook. So, so the application of this Landau functional, sort of unusual application, or non-trivial, or whatever you want to call it, that I wanted to discuss today is something called the domain wall. Okay, that in some ways makes contact with something we discussed earlier this week. So earlier this week, we had this topological classification of dislocations and defects in various phase transitions. And that was sort of completely general. It only depended on the symmetries of the order parameters, on how many dimensions you live in, and what the dimensionality of these defects is. But it didn't provide any details as to, like, how much energy or free energy does it cost to have one of these dislocations in a solid. And so that's one of the questions that the Landau functional can answer. And now, of course, the sense in which it answers it is that the Landau functional has these unknown parameters like A, B, and C in it, but you can in principle fix them by, for example, studying the behavior of the magnetization near TC. So the theory predicts it turns on as a square root, and if you measure the overall coefficient of this square root, then you measure some linear combination of A and B. So the way you can treat the Landau functional is that you make a bunch of measurements in the vicinity of TC. And after that, you view these coefficients as now having been fixed experimentally. And then you can go on and predict other stuff. And the domain wall is just an example of the other stuff that you can now predict. So, so spontaneous symmetry breaking implies that we had these two minima, plus or minus some M0. So these are the two minima. Okay. So you can imagine, and this indeed does happen in real magnets, that if there's no external field, as you cool through the phase transition, then the system locally makes a decision as to what minimum to go into, but globally they may not match up. And so you have these so-called domains in ferromagnets. And so the simplest kind of domain that you can think of is indeed, let's say on the left, all the spins are up. Okay, and on the right, all the spins are down. Okay, So then here it's plus m naught, and over here it's minus m naught. Okay. And then in the middle, of course, you have some kind of defect. Okay, and that would be the domain wall. So, so here it's drawn in terms of discrete spins, but if you draw the same thing in terms of discontinuous magnetization, then you locally average a little bit. So this will now be a smooth function. So the local magnetization will presumably look something like this. So it's minus m naught on the left and plus m naught on the right. So this is the magnetization as a function of distance as you go from left to right. Okay. So the beauty of the Landau functional is that it actually predicts, number one, what is the shape of this domain wall, including what is a typical width of this interface, and it predicts what the free energy cost of having a domain wall is. So that will, for example, determine how many domain walls you're likely to form if you take a piece of a magnet and cool it through TC. Okay. And so for that purpose, it's useful to take that Landau functional and rewrite it ever so slightly. So the functional was d3x gamma times the gradient of m squared alpha m squared plus beta m to the 4. Okay. But remember, we're interested now in the regime that alpha is negative. So for us, from now on, alpha will always be negative because these domain walls, they're a feature of the magnetized phase. So now we're in the phase that alpha is less than 0. Okay. So in this phase, the minimum of these constant terms, the ones that don't have a gradient in them, will occur away from 0. So this means the functional is really of this form. Oops. So I can write it, the gradient term is still the same. Okay. But the polynomial part I will now write as beta times m squared minus some kind of m naught squared plus some kind of constant that we don't actually care what it is. Okay. Now, you can easily check that I've just rewritten this polynomial term, so you can just multiply it out to check. So obviously this thing here, that's still beta m to the 4 minus 2 beta m naught squared m squared plus m naught to the 4. So so for this to work, it must be true that minus 2 beta m naught squared is the same as alpha. Okay, but that's of course precisely the condition we had before. So this must be equal to alpha, and that's just a way of saying that m naught squared is really minus alpha over 2 beta. Okay, that again is something we wrote down last week, last lecture on Monday. Okay, so so this is just a way of writing it that again makes it more apparent that the potential is of this form that I drew earlier. Okay, so for constant fields, again, we're now in the regime that it looks like this. Okay, this is plus m naught. This is minus m naught. Okay. Okie dokie. So I haven't really done anything. Okay. So so what the domain wall now is some kind of configuration that starts in the left minimum here. Okay. That's where the domain wall begins, but it ends up in the other minimum over here. Okay. So the domain wall is some kind of configuration that takes you from the left to the right. Okay. Now, in principle, of course, you can draw, infinitely many configurations that take you from the left to the right. but they will have different energy, because whenever you try to go, or different free energy, whenever you try to go from the left to the right, you have to do two things. I mean, number one, you're no longer in the minimum, as you, in this regime here, this regime here, you're not at the minimum of the potential. So there will be some free energy cost for not being at the minimum. In addition to that, in order to get from minus m naught to plus m naught, the gradient of m cannot be zero in this regime. So now you also have some cost in this gradient term. And so there will be a domain wall that has the lowest possible free energy, that somehow makes the best possible compromise of, in some ways you want to go as quickly as possible because you spend less and less volume in this regime where the constant terms are not zero. But if you go too quickly, then the gradient term is large. So the actual free energy will be some kind of compromise between the sort of potential term and this kind of gradient term, okay? So the goal is then the following. So there is a domain wall, there's a minimum free energy domain wall. Okay, and why do we want minimum free energy? Because again, free energy is like a Boltzmann factor. So the one with the lowest free energy is the one that you're most likely to find in an actual system. So there may always be thermal fluctuations that go to even higher free energies, but the one you're most likely to see is a domain wall that has the minimum possible free energy. Okay, so you can view this as the sort of variational problem that we've studied in mechanics. So what you can say is that we want the variation of the free energy to be equal to zero. That's what it means to sit at a minimum. And we want that subject to two boundary conditions, which is that it actually is a domain wall, meaning that m naught, m at minus x, well, at minus x goes to infinity, so at minus infinity is minus m naught, and m at plus infinity is plus m naught, okay? But we know how to do variational problems, so this is just a standard Euler-Lagrange kind of problem. So remember what A actually is. So again, A is d3x gamma times gradient m squared plus beta m squared minus m naught squared plus a constant, which we don't care about, okay? So, so we vary this A with respect to M. Okay. So number one, remember that inside, so this kind of variational derivative is like an ordinary derivative, except it acts inside an integral, okay? And if you have functions that are derivatives and so on, the way you can figure out how the variational derivative acts is you just integrate them by parts, okay? So this term gamma times the gradient of m squared, you can integrate this by parts. So you can always view this as just two identical terms. So this is gamma gradient m times gradient m, okay? So if I differentiate that, I just have, it's the standard product rule, you have the same term twice, so they will be a factor 2. And each one of them, you can always get rid of the gradient by just integrating by parts. So the variational derivative is then minus twice gamma times gradient squared of m, okay? And for the rest of the integral, this is like an ordinary derivative. So if I differentiate that, I get a factor of 2 from the chain rule, another factor 2 inside here from product rule. So this is 4 beta m squared minus m naught squared is equal to 0. Okay. So what is this? Well, this is now an ordinary differential equation that determines m. And in principle, of course, this is a three-dimensional, a three-dimensional problem. But we're looking for a solution that's just an ordinary domain ball. So we're looking for a solution of the form. So in principle, m is a function of x, y, and z. But we're looking for a solution that's of the form just m of x. Okay, so this is a flat, you could call this a flat domain wall, a domain wall that's somehow infinitely extended in the other two directions. Okay. Strictly speaking, once you're all done, you should check that that actually is the preferred free energy solution, that these domain walls have no tendency to lower their free energy by crumpling up. And loosely speaking, you can already see why that happens, because these gradient terms, they always contribute positively to the free energy. So if you can avoid gradients in terms of y and z, then that's probably a good idea. And again, physically, what it means is that the correct configuration looks something like this, that we have a three-dimensional box, really. This is our magnet. And inside this magnet, there's a flat domain wall. Okay, this is the x direction. This would somehow be y and z. Well, I'm not drawing this right. Okay. So this is the kind of ansatz we're making here. So if this is the ansatz we're making, then you end up with an ordinary kind of one-dimensional differential equation. So what is the differential equation? It's, again, I'm just writing it down again. So it's minus 2 gamma. So this is now really just the derivative in the x direction. And then plus 4 beta m squared minus m naught squared is equal to 0. And this is an ordinary differential equation for a function m of x, subject to these boundary conditions that I mentioned, that you go from m naught at minus infinity, minus m naught at minus infinity, to plus m naught at plus infinity. So, so this differential equation, of course, you can just solve it by, you load Mathematica or Maple, and you just put this in as a boundary condition that you want to start. You pick some, of course, not minus infinity. You pick minus 1700 and initialize it to minus m naught, and then you want to find a solution that goes to plus m naught. That actually requires a little bit of thought as to how exactly you do this, because, of course, if you just initialize it with minus m naught, just staying at minus m naught is always a solution. Okay, so so you have to think with it a little bit to find that solution that actually crosses over. So that requires a little bit of thought. But what is beautiful about this problem is that there actually is a way to find the solution analytically. And the easiest way to see this is actually to notice that what we just did looks an awful lot like ordinary classical mechanics. So, so this is the observation, that the whole thing looks like Newton's equation. So it looks like classical mechanics. And how do you see that it looks like classical mechanics? So in classical mechanics, we had an action principle where we found the Newton's equation by minimizing an action functional, and the action functional was an integral over time of the Lagrange function, and the Lagrange function was a half m x dot squared minus some kind of potential v of x. Okay, and now you can see what the analogy is to what Landau's free energy functional looks like. The analogy is that the thing that in classical mechanics is mx dot squared is now gamma times gradient x m squared. And the thing that in classical mechanics was minus v of x, okay, that is now plus beta m squared minus m naught squared squared. And the only thing that's slightly confusing here, okay, I don't know, maybe I should have used a variable other than m. In classical mechanics, m of course stands for mass and it's just a constant. And on the right-hand side, m of x is the magnetization. Okay. So I hope, I mean, that shouldn't be confusing, I hope, okay? So the thing that's kind of funny is that the analog of time is now space. So in Newton's equation, we solve a differential equation for x of t, okay? Now we're solving a differential equation for m of x, okay? So the variable that's being differentiated in one case was time, in the other case was x. The other issue is, of course, that in classical mechanics, x is a vector, but the integral is only over time. So the motion is always kind of one-dimensional. Whereas, of course, now the full Landau functional is actually a three-dimensional functional. So if you look for more complicated configurations, they're not just functions of x. In principle, they could have been functions of x, y, and z. But other than that, it's really a perfect analog, okay? Now, the one thing we learned in classical mechanics is, so you can now run the variational principle and the Euler-Lagrange equation in classical mechanics was, of course, Newton's equation. So, okay. So this thing, of course, implies Newton's equation, which is mx double dot is minus v prime of x, okay? And you can integrate this equation in much the same way that in principle you can integrate the equation on the top. So, so this here is just an ordinary second order differential equation, which you can integrate forward in time. And this up here, of course, is also just an ordinary second order differential equation, which you can integrate in space. But in classical mechanics, we learned a trick, which is that there's often a shortcut to integrating the second order differential equation, which is kind of easier because we're just integrating a first order differential equation. And that was based on the idea that energy is conserved. So let me remind you of the trick. Okay. So we saw in classical mechanics that if the potential is not a function of time, then the solution of the Euler-Lagrange equation implies that energy is constant. So energy is E is a half m x dot squared plus v of x, and that's constant, okay? And again, that was useful because you can solve that equation for x dot. And then all you have to do is integrate an equation for x dot, which is a first order differential equation rather than the second order differential equation. So what is the analog? I mean, since this is, you can always rename things and the arguments must still be perfectly valid. So this argument about energy conserved must still be valid after you rename all these quantities so that you get the ones that appear in the Landau theory. So in the Landau theory, it must therefore be true that the following thing is conserved. So there is some kind of function that's conserved, and I will call it kind of energy in quotes because it's not really energy. So it's the kinetic term, which was gamma times gradient m squared, plus a sort of potential term. But the potential term is now minus beta m squared minus m naught squared. So that must be constant. Okay. And the minus here is super crucial, as you will see in a second. The minus is super crucial. Again, where did it come from? It came from the fact that in our Landau functional, which of course is kind of on the previous page, on our Landau functional, this kind of potential term came with the positive sign because it was a contribution to free energy. But in the action in classical mechanics is T minus V. So the potential comes with a minus sign. So it comes from the fact that this is a minus sign in classical mechanics where we differentiate with respect to time. But in the Landau theory, where we differentiate with respect to space, the potential enters with a plus sign, okay? So that's kind of super crucial, okay? So let me make a new whiteboard and actually just write it down one more time. So what we now concluded was that this quantity, okay, again, let me maybe still write the quotes because this is not energy. It's just something that's conserved. Where constant, by the way, now means in classical mechanics, where the action functional is an integral over t, conserved means as a function of time. And here, this kind of energy is conserved as a function of space because m is a function of x, okay? But again, mathematically, the manipulations that show that it's conserved are exactly the same, okay? Now, but let's forget that this is really Landau theory. You know, again, let's just imagine this kind of problem is classical mechanics. So you can now sort of think of the analogous classical mechanics problem. So if this is classical mechanics, then this is some kind of point particle with some funny mass gamma. Again, remember that the derivative with respect to space in classical mechanics, it would be some kind of x dot. And then there would be a potential which is minus beta x squared minus some x naught squared squared. So this would be the classical mechanics problem where this here, okay, again, this quantity would be the potential energy. Okay, so let's just draw this classical mechanics problem. So this classical mechanics problem, okay, the direction is now x. Okay, and it has a potential which is some kind of polynomial potential. The only funny thing about the potential is it has a funny sign. Okay, the mass has the expected sign. Gamma is a positive coefficient, so this is a particle with a positive mass. The only thing that's funny about it is that it has a funny potential energy. So what does the potential energy look like? Well, it's the original free energy thing, but kind of flipped over. Because if interpreted as a potential, if interpreted as a potential in classical mechanics, it has kind of the wrong sign. Okay. So, so does that make sense? So this is again, this is kind of V of X in quotes because it's not really an ordinary potential. It's just what the potential would look like if we think of the analog classical mechanics problem. Okay. So the kind of solution we're trying to find, which in the real problem is a solution as a function of time, as a function of space, in the classical mechanics analog problem, a function of time, is the one that goes from one minimum to the other. So the solution we're trying to find is one that goes from here at time equals minus infinity to here at time equals plus infinity, okay? And that is indeed a possible classical motion of the system because this ball can just roll down one hill and roll back up the other, okay? So this motion is certainly possible. So this motion is simply, it starts very slowly, it rolls down the hill, and then it rolls back up, okay? In the classical mechanics problem, it would be hard to understand why exactly it would stay there once it gets up. But we're just trying to solve a differential equation. The actual problem is with the one with the free energy, where free energy determines where you stay, and ultimately this is one of the minima. That's why you're staying. Okay, so we're just using the classical mechanics analogy to figure out what the solution of the differential equation is. So okay, so how do we apply this method now? So we're applying. So what this shows, by the way, this argument that I just gave, is that the kind of motion that we're studying, which is a motion that starts in one minimum initially and then goes to the other minimum, it not only takes place at constant energy, it takes place at constant zero energy, because it goes from, this point over here to the one on the other side. So initially there's no, this analog ball that's rolling down initially has no kinetic energy, it has all potential energy. And then you see from the picture that the potential energy it starts at is actually zero potential energy. So this calligraphic E, which is the analog energy, not only is it constant, it's actually zero. So we conclude that what we have to solve is that gamma dxm squared is just equal to beta. I think I lost factors of 2 at some point, didn't I? No, I didn't. Okay. Okay. So we just want to solve this. And now I can just go ahead and solve. So this means that dxm is square root of beta over gamma times, strictly speaking, plus or minus m squared minus m naught squared. Okay. But what have we gained? Well, what we've gained is that this is now an ordinary first order differential equation, which you can just integrate, So this was our little spiel in classical mechanics, that loosely speaking, once you reduce things to ordinary first order equations, then formally you can always find a solution by integrating. Okay. So so you can, by the way, pick the correct sign here. So the correct sign here, let's try to think about that. So the particular solution that we're trying to find is one that looks roughly like this. Okay, so you see that in this solution, dxm is actually always greater than 0. It never slopes down, it only slopes up. And you also see that, so this is minus m naught. Okay, this is plus m naught. So you can see that m squared in this problem is always less or equal to m naught squared. And so I think this means I must pick the minus sign, because the m squared minus m naught squared is always a negative quantity, but the derivative of m, I want this to be a positive quantity. So I think in order to get the right solution, I have to pick the minus. Okay. Okay, so let's make a new whiteboard. So just to write it down one more time, so the thing we were solving was dxm is square root of beta over gamma, and we decided that this should be m naught squared minus m squared. Okay. So dxm is just dm by dx. Okay. So formally, I just integrate this now. So I can, I imagine that I integrate the left side and the right side. So then on the left side, I get an integral that's dm over m naught squared minus m squared. And on the right-hand side, I get an integral which is root beta over gamma dx. Okay. And we also know what the boundaries of these integrals are. Okay. So you start in the minimum minus m naught at x is minus infinity, and then you get to some m at x. Okay, if you want to be more careful, this should be some kind of m tilde. So this is the boundary of an integration, and m is the integration variable. Okay, does that make sense? So on the right, of course, we can directly integrate this. So this just gives so on the right, you just get root beta over gamma as x. On the left, what you get is some kind of integral that I think is an arctang. And if you pick the boundaries correctly, then I think what you get is the following. So you get that beta over gamma times x. I mean, strictly speaking, x minus infinity, but the integral on the left also diverges. So if you pick the right boundaries, you find that this is 1 over m naught times the arctang. So this is now just doing an integral. Okay. And actually, I don't even want to solve it like this. So now I solved it for x, but this is, again, the classical mechanics, where the last step in these kind of, we converted it to a first order differential equation, and then we solved that one by integrating. But the last step in all these exercises was always that we had to invert the function, because you solve it for t as a function of x, and you really want x of t. And here we solved it for x as a function of m, but really what we want is m as a function of x. So, so really I should have solved it the other way around. Okay, so I get that m is equal to m naught times the hyperbolic tangent of m naught times x times root beta over gamma. And I can go back to my notes and find what m naught was. So m naught was some alpha, or root alpha over 2 beta. Alpha is actually negative. So this is the absolute magnitude of alpha. So this means that m naught times root beta over gamma is actually, the beta goes out. So this is the square root of alpha over 2 times gamma. Okay. So this is kind of cool. So we actually managed to solve this equation analytically. Okay, let's begin the whiteboard. So, okay, let me just write it down one more time. So m was m naught of hyperbolic tang of, and I think we now decided, so it's really alpha over 2 gamma that appears in there. Times x. So if you were to plot this, what would that look like? Okay, so tang is indeed a function that goes from minus something to plus something, I hope. This function goes from minus m naught to plus m naught as a function of x. So, so this is a famous solution. So number one, in our context, this solution is called the domain wall. But interestingly enough, I mean, just a purely polynomial potential, of course, that's kind of generic. So, so this particular differential equation actually appears in all sorts of contexts. And in various other contexts, the exact same solution, this kind of something depends as a hyperbolic tangent of some other variable, also appears. And so in these other contexts, the same solution sometimes has different names. So in other contexts, the same solution is either known as the kink. So the solution is sometimes discussed as a soliton in certain scalar field theories. And in this context, it's known as the kink. And the solution also appears as a semi-classical solution in certain quantum mechanical systems. And in that context, this solution is known as the instanton. So that actually is a context where the solution is viewed as a function of time. Why it's called instanton. It happens at some certain time. Okay. So, so one of the first things, by the way, that we can read off from this is you can ask again, microscopically, you might think that the spins just, there's one layer of spins all up and then the next layer over, it's all down. But typically in the vicinity of TC, it's more complicated than that, that you go away from the domain wall and they're really all up. And then as you get closer, there's some that start to flip, and then eventually you get to the point where they all flip. So the domain wall actually does have a certain width. And from the solution, you can now kind of read off what that width actually is. So hyperbolic tan is just some kind of function. So that doesn't depend on any parameters. So the width of the hyperbolic tan function is just 1/2. It's just some number of order 1. It's the width over which it turns over. So this means that the width in X of this solution is just root 2 gamma divided by alpha. So the width of the domain wall, which is just the range in X over which it turns over, is just of order 2 gamma divided by alpha. Okay. And now you can remember that gamma is some kind of constant. So gamma was some kind of constant plus terms of order t minus tc. But alpha vanishes near the phase transition. So alpha was some kind of constant of the form t minus tc plus higher order terms. So one of the first predictions of this theory is that the width of the domain wall goes like 1 over the square root of t minus tc. Okay. So this is something that in principle you can check. I mean, you can try to take images of ferromagnetic domain walls and see if you can see something about the width of these ferromagnetic domain walls, if they really become more diffuse as you approach TC, and indeed they do. So another question that you can ask, which is even more important, is, so now that we have this magic solution, you can ask yourself, what is the actual free energy cost of this thing? Okay, so let's make a new whiteboard. Okay, so what was the free energy again? So the free energy was d3x actually let's write it in this form. Okay, and so our domain wall was purely one-dimensional, so it was totally flat in the other two. So since the total free energy is an integral over all 3 dimensions, so 2 of them will just trivially give you a factor of the total area of the domain wall. So so this will trivially be proportional to the area of the domain wall times an integral over x. And so now that m of x is given, this is an integral that you can just compute. There's sort of one minor trick that you can employ, which is that remember that the solution we found, it was found by means of a trick, which was the trick was that this kind of analog energy was 0, and the analog energy that was kind of the sum of the two terms with the sort of minus sign thrown in. It was the sum of these two terms. So so that means that as a contribution to the free energy, they actually now contribute equally. So you can compute the total free energy by just computing twice the first term, or you can compute twice the second term. So at the place, one way to think about this, which actually makes a whole lot of sense, is that at the place where you minimize the free energy, these two contributions to it, the one that comes from the gradients and the one that comes kind of from potential energy, they actually contribute equally. Okay. So, so this means that the total free energy is just twice the area times an integral over x. This goes from minus infinity to plus infinity of gamma times this. Okay. And this integral, so what was m? So m was m naught times some kind of hyperbolic tangent of, where did it go? So it was beta over 2 alpha times x, okay? So this means if you differentiate, so the xm will go as m naught beta 2 alpha times whatever the derivative of tangent actually is. Okay. So, okay. So this means the total free energy goes as twice the area. Okay. You will have a factor m naught squared. You will have a factor m over 2 alpha. And then there's this integral that we have to compute of the derivative of tangent. Something like this, okay? So what I'm trying to do here is trying to show that you can extract all the constants and just reduce it to some kind of integral that you have to do. So the way you extract all the constants is, number one, what was m naught squared again? Okay, maybe I can locate it in my notes. It's alpha over 2 beta. Okay, so this would seem to go out. Did I do that right? Okay. I lost the factor of gamma, didn't I? So there was still a gamma here. And the factor inside the tangent, let's just look to make sure. Was, oh, it's alpha over 2 gamma, so I did this wrong. Okay. The factor inside the tangent, I made a mistake. Okay, So, so then I should be able to do a change of variables. So I should be able to call this quantity inside the integral, say, x bar. So x bar is alpha over 2 gamma times x. So that dx is 2 gamma over alpha times dx bar, okay? So now we can try to collect the constants. So the constants that appear are, there's twice the area, then we have a factor of alpha over 2 beta, we have a factor of gamma, and then from changing variables inside the integral, we would seem to get a factor of 2 gamma over alpha. Oh, sorry. Okay, so let's do it even more slowly. So we had an alpha over 2 beta. So this was the alpha over 2 beta. So then I have to write down this one, which is alpha over 2 gamma. Okay, then there's a factor of gamma, and then there's the factor from changing variables inside the integral. So that's 2 gamma over alpha. Okay, so the net factor would seem to be, let's change colors again. So this constant, let's forget about factors of 2. So it's proportional to the area. It's proportional to alpha to the 3/2. It's inversely proportional to beta. And it's proportional to gamma to the 1/2. Okay. And then there is some remaining integral. So the integral some integral dx bar over the derivative of hyperbolic tang squared. And okay, so I think that derivative is some kind of hyperbolic secant function squared. And so overall, this becomes some integral over hyperbolic secants to the 4th power. And that I just punched into Mathematica yesterday. And so that integral is 4/3 according to my notes. Okay. So then the overall result is that the total free energy of a domain wall is proportional to the area. And then the remaining factors is there's a 4/3 over root 2. And then there's a scaling, which is gamma to the 1/2 alpha gamma to the 1/2 alpha to the 3/2 divided by beta. Okay. So, so what do we conclude from this? Well, number one, the total free energy cost of having a domain wall is obviously proportional to the area of the domain wall. Okay, that makes a great deal of sense. It's more expensive to have a big one compared to a small one. And remember, among these various constants, the one that depends on temperature is alpha. So this free energy of a domain wall, so A divided by the area, it scales as T minus Tc to the 3/2. And that's actually kind of important. So it means that as you approach the phase transition, it becomes cheaper and cheaper to have a domain wall. And so that's indeed now one possibility for thinking about how these phase transitions happen in the first place, that that as you approach the phase transition, now the tendency of the spins to align somewhere becomes bigger and bigger. So they want to form little domains in which they're locally aligned. That somehow optimizes their energy. But the cost of being locally aligned is that you're still immersed in some sea of spins that do other stuff. So roughly speaking, in order to locally have a domain where the spins are aligned, you always pay a free energy cost, which is the cost of having this domain wall. Okay? And so number one, you see, of course, that it's always cheaper to make a small bubble compared to a big bubble because there's some area cost. But you also see that it becomes easier and easier as to get close to DC. So one way of thinking about the phase transition is that it can happen by kind of nucleating small bubbles, and the main cost you pay is the price of having one of these domain walls, but that vanishes as you get closer and closer to TC. Okay, so let me just draw a few more pictures. Okay, picture number one, okay, that in some sense we of course already discussed. So again, the solution that we now found. So this is M of X. But now we also computed the free energy cost of a thing like this, so I can plot the free energy density that goes along with this kind of solution. So as a function of X, I can plot the free energy density. And as you get far and far away from the domain wall, it's in the local minimum of the constant part of the free energy, so there's no free energy cost associated with that. There's also no gradients. So as you get sufficiently far away, the free energy density goes to 0. And so the actual free energy density is somehow peaked. Okay. Near the location of the domain wall. So the domain wall has some width. And of course, that's the same width as the width of this kind of free energy density. So the domain wall has some free energy cost. That free energy is effectively stored in some width delta x around the actual domain wall. Okay, for a domain wall to have a free energy that's proportional to its area, again, it means that the free energy divided by area is some kind of constant. So let me write this down one more time. So we effectively already said that. So A free energy divided by area is some kind of constant. And so that free energy has the same units as energy. So this is some kind of energy per unit area, which is sometimes called a wall tension or a bubble tension or a surface tension. Okay. So anything that's an energy per unit length or an energy per unit area, you can call that a tension. And it's an energy density or a free energy density that effectively is the thing that's trying to keep this wall straight. And that actually, the most famous system, of course, where things like this occur is ordinary water, where you can have bubbles of vapor inside the liquid. And again, ordinary water, these bubbles have a surface, which is the surface that forms the boundary between the two phases. And there's an energy cost, just like there's an energy cost in the magnet, there's an energy cost associated with having that interface. And the fact that there is a positive energy associated with it is the one that minimizes the surface area of these droplets, because again, there's a finite wall tension, and that's the thing that somehow keeps them as smooth as possible. And as I mentioned, this is more than just a mere analogy, because the free energy functional for the Ising model is actually the same as the free energy functional that you encounter in the vicinity of the liquid gas phase transition. So this is again the picture that I already drew earlier. So in water, okay, we have this phase diagram. So in water, this is pressure and this is temperature. And we have a phase diagram that looks something like this. Okay, where so this is the solid, this is the vapor, and this is the liquid. Okay. Sorry. At low pressure, at high pressure, you have to, it's the other way around. But in the vicinity of this liquid vapor endpoint, again, the symmetries of the theory are the same as the symmetries of the Ising model. So you can write an analogous kind of Landau functional where you just replace the magnetization by the difference in density between the liquid and the vapor phase. Okay, and so when you do that, then the very same functional will again have these kind of Ising domain walls, except that now they're really bubble walls separating the liquid and the vapor phase of ordinary water. And so the same theory will then predict that you have a surface tension between liquid and water. You cannot predict its absolute magnitude, but you can predict that that surface tension scales as temperature minus critical temperature to the 3/2. So that's actually that's a pretty remarkable prediction that you get out of this theory. Okay. So near the liquid vapor endpoint, okay, you can write, delta rho of x is the density minus the density at the endpoint. And then you have a free energy functional okay, like so. And so this functional will then have solutions that have exactly the same form than the ones we just discussed. So there will be some kind of solution where this is now delta rho of x. And so on the left-hand side, it's underdense, so you're in the vapor phase. And out here, you're in the liquid phase, you're overdense, okay? And in the middle, you have a bubble wall. Okay. And we saw that the bubble wall has a tension which goes as T minus Tc to the 3/2. Okay. And indeed, that's an important ingredient if you somehow study nucleation of bubbles in water, that you get this out of the Landau theory. So we have kind of 3 minutes. Maybe let me make one more remark again about the same theory that we're studying here is, again, that's maybe a sort of obvious observation, but I want to say that maybe explicitly. So here again is our favorite solution, the domain wall, the kink, whatever you want to call it. So m of x is a function of x, okay? And remember that what the solution does is it sits in a free energy minimum over here, and then it sits in another free energy minimum over there. So this was minus m naught. This is plus m naught. Okay. So, so this is a domain wall where you go from minus m naught to plus m naught. You could ask yourself, why doesn't that domain wall just disappear? Okay, so for that domain wall to disappear, all the spins on the right-hand side of the domain wall, they would all have to flip, okay? This thing to disappear. So all of this stuff would have to flip to the other side. And so you can ask yourself, how likely is that to happen? Well, again, there's a sort of Boltzmann factor for that to happen. And it's just e to the minus free energy of doing that, okay? But the free energy cost of doing that is that everywhere on the right half plane, the magnetization has to go from that one minimum over the hump in the middle to the other minimum. So here's our free energy functional again. Okay. For the spins to do that, they have to go from here to here. But the only way to do that is to climb over the hill. That's what they have to do. So this is a free energy density. So there's a finite free energy per unit volume associated with doing that. So in order to do that in the entire right half plane, that requires an infinite amount of free energy. And that's why it doesn't happen. So if you actually have a truly infinitely extended domain wall, it cannot disappear because it costs an infinite amount of free energy for that domain wall to go away, okay? And so effectively the fact that there were two minima in this free energy functional, that is the thing that prevents this domain wall or this defect or this dislocation from going away. So previously we had this kind of topological classification that you could label defects by these discrete numbers, and they were truly different because they corresponded to certain paths and order parameter space that you couldn't continuously deform. So here this Landau functional that remembers that this is that a single domain wall is kind of topologically stable because it comes from one minimum and goes to another minimum, but it's sort of energetically stable because to actually deform it so that it sits in the same minimum everywhere is an infinite amount of free energy because that object is infinitely extended. You know, it goes to one minimum at minus infinity, another minimum at plus infinity. So, so this costs an infinite amount of free energy. Infinite. And so the domain wall is, and indeed, again, it's sometimes called topologically because it has these two different vacua that you cannot continuously deform, stable. Okay. However, of course, you can not only have domain walls, you can have anti-domain walls. So you can have a configuration. Looks like this. So this, again, the magnetization is a function of x. And you can now have an object that is effectively a domain wall, okay, followed by an anti-domain wall. Oops, not drawing this super well. Okay. And this object can just disappear because the domain wall on the left, I can always just move it a little bit to the right. That costs just a little bit of free energy because I have to set the whole thing in motion, but you can do that arbitrarily slowly. In the domain wall, the free energy of having a domain wall is independent of the location of where it is. So you can always take it and just move it very, very slowly. So you can obviously take the domain wall on the left and very slowly move it to the domain wall on the right, and then they will just disappear. So there's, if you wish, a series of configurations where they just move closer and closer together. And of course, eventually they just disappear. Okay. So this is the process of annihilation of two domain walls. So if you have a domain wall and an anti-domain wall, then they can just annihilate. Okie dokie. So this is somehow all I truly wanted to do today. I think it's a really nice application of this kind of Landau functional. It makes contact to a lot of other stuff. As I say, the same kind of solution appears in many different fields of physics. It appears in the study of solitons and so on. It's actually quite useful, and we'll get back to that a little bit in, again, understanding first order phase transitions via nucleation of bubble walls. So it's exactly this sort of functional that predicts all sorts of scaling laws in the vicinity of such a transition.